Here in 13.1, we're going to touch just a little bit on a big topic called conic sections. There really actually are 4 conic sections, and the way in which they're all related is they're all related to taking a cone and slicing it. In fact, if you go to the root words, that's what these words mean. Conic means of or related to a cone, and section means to slice something up, cross sections, that type of thing. So if you take a cone and you slice it, if you section it different ways, you get different shapes. If you slice it perfectly horizontally, like this here, you get a circle. If you slice it at a very slight angle, you get an ellipse. But as your angle gets bigger and bigger and bigger, eventually you're slicing at such a great angle that your ellipse doesn't quite close up at the other end. It goes on forever down that way, and that's where you get a parabola. And if you continue past that point, the parabola ends up so wide and straight-sided down at the end that it's not even really a parabola anymore. It's something called a hyperbola. And one other way to link all of these ideas together is that all of these different shapes can also be the paths of things that are orbiting, like planets or spacecraft or moons or things like that. A circle would be sort of a perfect orbit where you never go any higher or lower or further or closer to the sun. An ellipse is a bigger orbit. And then if you've got a whole lot of speed, your orbit doesn't actually close up. You get what's called escape velocity, and your orbit is a parabola and it never comes back around again. And if you go even faster than a parabolic orbit, you get a hyperbolic orbit. So you can think of these as all being slices of a cone, or alternatively, if you're thinking a little more about space, you can also say these are all orbits. The only ones we're going to study here today are circles and parabolas. The other ones are more complicated. These are the ones that will give you sort of an introduction to this idea, and honestly, they're the ones that are more practical. Parabolas are something we've already seen in a couple of different ways before, and circles are definitely practical, like wheels, gears, the round things are a very common part of life all over the place. Ellipses, hyperbolas, not nearly as common, not nearly as practical. So we'll start with parabolas because we've kind of already studied them in the past, and we're going to change things up a little bit. In the past, when we studied parabolas, the way we were introduced to them, they looked like this. They had some sort of a squared term. You would have ax squared plus bx plus c. Y was equal to that, and you would get a graph. And you should remember generally what those graphs look like. They're sort of an archy kind of a shape, and they go up or down based on whether a is positive or negative. The change we're going to make today is we're going to consider what happens if you switch the letters around. Instead of having x squared, what if you had y squared? What if y did what x used to do, and x does what y used to do? And what that does is a very minor change visually, but a pretty major change in terms of the geometry. This will end up giving you a parabola that will go horizontally. In other words, instead of pointing up and down in the y direction, it'll point left and right in the x direction. So it'll either look like this, or it'll look like this, sideways. So you could have normal parabolas pointing up and down, sideways parabolas pointing left and right. So we need to practice those new sideways ones. We don't really need to practice the up and down ones. We've done those plenty of times in the past. So we're going to practice graphing that kind of thing here. Notice, aside from the fact that y is where x used to be and x is where y used to be, it looks pretty much like your normal sort of a parabola type of equation. And what you should be thinking is, okay, to graph parabolas, step 1 is find the vertex. So we're going to try and find the vertex here. And you could use completing the square, but we're going to go a little quicker than that. We're going to use the vertex shortcut. And the vertex shortcut used to be x equals negative b over 2a. But remember, x and y have sort of switched jobs. Y is where x used to be, x is where y used to be. So the shortcut isn't going to be x equals negative b over 2a, it'll be y equals negative b over 2a. But aside from that, the shortcut will work exactly the way it used to work. Negative b over 2 times a gives us negative 1, and that's, be careful, negative 1 for the y coordinate. And then to get the x coordinate, you've got to plug in for y. So x is going to be negative 2y squared minus 4y plus 1. And we're going to plug negative 1 in for y. So that's going to be, let's see, negative 2 plus 4 plus 1. That's going to be 3. Over here on the right, I'm going to make a little table of values so that I can draw a nice, accurate picture. And the first point that I'm going to draw is the one we just figured out, that the vertex has an x-coordinate of 3 and a y-coordinate of negative 1. So it's right there. Now all of your instincts are telling you that this graph is going to point up or down, but remember, this is a horizontal parabola. What you should be imagining is either it's going to point to the right or to the left, one or the other. You might even have an instinct about which direction it's going to point, but let's let that sort of crop up automatically. In order to graph this thing accurately, we're going to plug in some more points, just like we used to do. We're going to use a table of values. But the difference is, I really don't want to plug in for x in this equation. If I try to plug in over here and solve for y, that sounds like a lot of work. It would be a lot easier to plug in for y and solve for x, because then I just have to compute out the arithmetic. So I'm going to plug in y-coordinates that are close to negative 1, like 0 or negative 2 or 1 or negative 3, that kind of thing. You know, y-coordinates that are close by so that my points don't end up really far off or maybe not even on my graph. So pause the video for a second, actually plug those numbers in, see if you get the same results as me. So here, plugging in 0, we get 1. That's pretty easy because 0, 0 plus 1. Plug in negative 2, you'll also get 1. And remember, parabolas are supposed to be symmetric. That shouldn't surprise you. If you plug in 1, you get negative 5. And if you plug in negative 3, you also get negative 5, again, because these things are supposed to be symmetric. And if we plot these 4 new points, 1, 2, 3, 4, 5, 1, we get a point there. 1, 0, we get a point there. 1, negative 2, we get a point there. Negative 5, negative 3, we get a point there. And look at how that thing is arranged. Just like I kind of told you it would be. It's a sideways parabola pointing to, it turns out, to the left. You might have guessed that it was pointing to the left because we have a negative a value, negative coefficient on the squared term. And if that's what you guessed right. That is exactly what it does. It points to the left. So for the most part, parabolas will be pretty much like they used to be, except for these ones here where the x's and y's are switched around. But other than that, you treat them just like normal ones. Find the vertex, make a table of values. So now let's focus on circles, because that's a new type of a thing. So the key idea with circles is that with a circle, you've got a geometrically simple type of thing that ends up with a relatively complicated looking equation. So geometrically, the geometry definition for a circle is a pretty simple one. It basically says the distance from the center needs to be a fixed number. So the distance from HK, because that's the coordinates I'm going to use for my center, the distance from HK to any point on the circle is some number which we're going to call r. And you should know why I'm going to call it r. The word for that distance is radius, so r for radius sounds like a pretty sensible thing to do. So when we say distance, and we're looking at something where we have coordinates, we should be thinking about the distance formula. So the distance formula, remember, is kind of a mess. It's this big giant square root where it's x2 minus x1 parentheses squared plus y2 minus y1 parentheses squared equals the distance d. Well, in this case, we've got almost everything we need to just simply plug sort of robotically in to that distance formula, except for one little thing. I know the coordinate at this end of the radius is hk, but the coordinate over here can be any point on the circle. It doesn't have to be up and to the right at that specific spot. Any point around here would give you the exact same distance. So the point at this end of the radius has to be variables. Because it's not just one point where the distances are, it's all of the points where the distances are. So we got variables at that end of the radius, specific numbers at this end of the radius, and the distance there has to be r. Let's plug that all into this formula here and see what we get. Get a big old square root. Let me put in all the standard stuff. We're going to have r over there. x2 is just plain x. x1 is h. y2 is just plain y. y1 is k. And there you go. That's the equation for a circle. Well, not really. I'm lying a little bit. The actual equation for the circle is that with a very slight modification. There's the tiniest little change you make. All you do is you get rid of the giant square root. So if you look at the formula for a circle and you think it's really, really complicated, understand that it's actually just the distance formula with the tiniest little modification. You just clear out the square root by squaring both sides. So don't be intimidated. That's what I'm saying. It's based on a formula you already know. The hard part of working with circles is similar to the hard part we had working with parabolas. And that is that equations are not usually left in this sort of a form. There's this idea of simplest form where everything gets multiplied out. So really, your typical circle equation will have that x minus h squared out, and the y minus k will be squared out, foiling things out, collecting like terms, getting it all equal to 0. So a typical circle equation would look more like this. Which means that if you're trying to graph a circle, you're going to have to convert it from this form back into the other form. Here's how that goes. Start out by grouping the x stuff together, because when you're all done, you should have x minus h squared. So all the x stuff should be together. Do the same sort of thing with the y stuff. Put all the y stuff together, because eventually it's going to be a whole bunch of y stuff together. And move any constants that are floating around in your equation over to the other side, like in this case, the 8. We're going to kick it over. And what you're trying to get is something parentheses squared for x and something parentheses squared for y. If your alarm bells in your head are going off, it's because I think you know what comes now. We're going to have to do completing the square. We're trying to make a parentheses squared. We're going to have to do completing the square. So for the x's, if that's a minus 8, there will be a minus 4 here, which means to make that perfect square we'd have to add 16, and if you add 16 on the left side of the equation, you have to add 16 on the right side of the equation. Then you do the same sort of thing with the y's. If that's plus 2, then we're going to have a plus 1 there. 1 squared is 1 that we have to add on both sides. So the right-hand side here ends up being 9 altogether. Now we can compare with the actual formula for a circle and identify the parts that we need to find. For example, we should be able to figure out what the center is, and we should be able to figure out what the radius is. So by comparing, it looks like h is 4. Be careful here, k, since it's supposed to be y minus k, but this says y plus, it looks like k is negative 1. Minus negative 1 is why we ended up with plus 1. The radius squared is 9, so the radius itself is 3. Once you can figure out what the center is and what the radius is, you should be pretty ready to graph the thing. So here, 4, negative 1, that's the center of the circle. and then the radius is 3, what we should do is go 3 in every direction and plot every point that's distance from the center. Now that's really hard to do except for 4 points. There are 4 really easy points where you can measure a distance of 3 and plot them very accurately, so please start with those 4. And then plot all the other ones where the distance is 3. And if you want to be super accurate, you're going to have to get one of these little compass tools that'll let you draw a perfect circle. But if you do it freehand, please put at least a little bit of effort into trying to draw a decent circle. We are going to have some artistic standards. If you've got 4 points that are supposed to form a circle, and you draw me something like this, I'm not going to give you full credit. You should be ashamed of yourself. That's not okay. What I want you to do is at least try. Put some effort in. I don't expect you to be perfect. I mean, take a look at the one that I drew up here. Is that perfect? Oh, heck no. This right-hand side over here is kind of dented in looking, and I kind of went too far over there, so my picture wasn't perfect. I don't expect yours to be perfect. But something like this, that's just lazy. Don't be lazy. At least try to draw a good circle. So, for circles, completing the square to get it in the right form, read off where the center and radius are. Be careful with plus or minus signs. Get at least 4 points drawn accurately, because those ones you have no excuse for. They're easy. And then connect the dots with something that is not shamefully bad.